This video looks at how the flap and gear rules are determined. We will start with flaps. First, a little background on early flap procedures. Early general aviation trainers did not have flaps. Since traffic was not usually an issue, most traffic patterns consisted of reducing the throttle to idle on downwind leg opposite the touchdown point, slowing to final approach speed, and adjusting the traffic pattern size to touchdown on the desired spot. When flaps first appeared, pilots were usually told only that they reduced stall speed and that they should be extended before landing. Let's join a pilot on his first approach in an airplane with flaps. He is now on his usual gliding final approach when he remembers that he is supposed to lower the flaps before landing. Selecting full flaps, he notices a loss in airspeed and immediately lowers the nose in order to maintain his approach speed. But now he is aware that his approach angle is much steeper than before, and he will be landing short if he does not apply power. After initiating a go-around, he is aware that he has learned something about the use of flaps. What did this experience teach him? He learned that flaps steepened his approach angle, and that he should not use flaps unless he has the runway made. In addition, since he was not taught that flaps decrease the touchdown pitch attitude, he was finding it difficult to make a good landing with flaps. Consequently, he decided that normal landings should be made without flaps, and that flaps should be used only if he was high on final approach. This line of reasoning was very common in the early days and can still be heard in some places even today. However, this experience did lead to one use of flaps. If high during an engine-out forced landing approach, flaps will steepen the approach if the nose is lowered in order to maintain the same airspeed. But what would happen if we are at a higher airspeed and apply flaps without changing the pitch attitude? The next video will tell us. This light airplane is in level flight at 190 knots with a pitch attitude of 0.6 degrees and a power setting of 27 inches of manifold pressure. We will now set half flaps while maintaining the pitch attitude and power setting constant. Note the large reduction in airspeed and the initial bump in the flight path. Also note that after the speed change stops, the flight path direction is approximately the same as before. At this point, we will apply full flaps. Note the similar result. Now let's repeat this sequence in a descent. This pitch and power setting will stabilize the aircraft at 90 knots and a 3-degree descent when full flaps are selected. It is important to note that the bumps during a descent are much smaller than the bumps at higher power settings. This demonstration showed the most useful application of flaps. Flaps are very effective for slowing down with little change in the final flight path direction, while maintaining the same pitch attitude. In addition, the flight path bumps are not only smaller during the descent, but they are of little consequence during non-precision descents. Now let's examine the reasons behind these results. Lift and drag depend on three factors: shape of the airfoil and wing, angle of attack, and airspeed. When flaps are extended, the change in the chord line increases the angle of attack, and the airfoil changes to a more efficient low-speed shape. Before any change in airspeed, lift and drag are both increased. What happens now can be seen in the following video. This simulator has the ability to show the forces acting on the airplane, both numerically and graphically. The box at the bottom of the screen shows the forces acting on the aircraft. The top row shows the forces acting perpendicular to the flight path, and the bottom row shows the forces parallel to the flight path. By definition, lift is the component of the total aerodynamic force on the aircraft which is perpendicular to the flight path, while drag is the component parallel to the flight path. The top row shows how lift, the perpendicular component of weight, and the perpendicular component of thrust combine to form the total force perpendicular to the flight path. Likewise, the bottom row shows how drag, the parallel component of weight, and the parallel component of thrust form the total force parallel to the flight path. The force picture shows lift in blue, weight in black, drag in red, and thrust in green. In order to show the effects more clearly, the scale of the drag and thrust vectors has been expanded, and the flight path shown as a magenta line has its direction considerably amplified. However, the numbers shown in the boxes are accurate. As we are in level flight at 190 knots, notice that lift balances weight and thrust balances drag, and the flight path remains horizontal. At 20 miles, we will extend full flaps. As flaps are extended, note the increase in lift and the resulting acceleration upward of the flight path, as well as the increase in drag. The increase in the flight path angle reduces the angle of attack, which reduces lift and stops any further increase in the upward direction of the flight path. Now the rearward component of weight and the increase in drag reduces the airspeed, which reduces lift and causes the flight path to begin to change in the downward direction. As the flight path approaches the horizontal, there is less rearward component of weight and reduced drag, which slows the airspeed reduction and the downward direction of the flight path. As the flight path reaches its original direction, note that the increase in lift and drag caused by the extension of full flaps has now been decreased by the reduction in airspeed. Finally, when lift balances weight and thrust balances drag, the flight path direction stabilizes close to its initial direction. If drag is the same as before, the final flight path matches the original direction. In any case, the final direction is usually close to the original, since it takes almost a 20% change in drag to change the final flight path by 1 degree, since weight is typically 10 times greater than drag. We are now ready to formulate the flap rule. Both the flap and gear rules are based on the principle of making configuration changes with a minimum change in pitch attitude and power. This principle maintains aircraft stability, reduces pilot workload, and enhances passenger comfort and confidence. This is the flap rule. Extend flaps to slow down while maintaining a constant pitch, attitude, and power setting, preferably during a non-precision descent. We can now look at a typical application of the rule, the use of flaps to slow down during a visual approach for a typical light airplane. The first step is to find the pitch, attitude, and power setting for the final approach with full flaps. We now will reduce thrust and apply full flaps. Then we will adjust pitch and power to maintain the target final approach speed of 65 knots and the rate of descent for a 3-degree final approach angle, which can be found by multiplying the final approach speed in knots by 5.3. At 65 knots, the rate of descent is approximately 350 feet per minute. When the airspeed and rate of descent stabilize, we see that the final approach pitch, attitude, and power setting is 0 degrees pitch, attitude, and 2100 RPM. Using this information, let's apply the flap rule to a simulated visual approach. In this fixed-gear light airplane, we are approaching the runway in level flight at 120 knots. We begin the descent by setting the final approach conditions of 0 degrees pitch, attitude, and 2100 RPM. Then, since we are below the max flap extension speed for the first notch of flaps, we maintain this pitch, attitude, and power setting and extend 10 degrees of flaps. After the airspeed stabilizes at 97 knots, we will extend 20 degrees of flaps. Maintaining the target pitch, attitude, and power setting, the airspeed stabilizes at 75 knots. Finally, we apply full flaps, and the airspeed stabilizes at 65 knots in a 3-degree descent angle. As we get closer to the runway, any necessary fine-tuning of our approach path is made with small pitch attitude changes, while coordinating power adjustments to keep the airspeed at 65 knots. Details of this procedure can be found in the pitch and power control video. Now that we understand the use of flaps, let's examine the use of the landing gear. The major difference between flaps and gear extension is that while flaps increase both lift and drag, gear extension increases only drag. Let's see how this affects both airspeed and flight path. This light airplane is in level flight at 90 knots with full flaps. If we extend the landing gear while maintaining the same pitch, attitude, and power setting, we see about an 8-knot reduction in airspeed and a slightly less than 2-degree angle of descent, neither of which is very useful. However, if we would like to utilize the gear's ability to initiate a useful descent, a change in pitch, attitude, and power setting will be necessary. But couldn't we also initiate a descent with flaps? Yes, but with a large change in pitch, attitude, and a bump in the flight path due to the higher initial airspeed required, since full flaps must be extended prior to slowing to the final approach speed. If we extend the gear prior to the descent point, a large power increase is necessary to maintain airspeed, followed by a large decrease in power to initiate the descent angle. Also, without a definite point to extend the gear, the probability of forgetting to lower the gear is increased. The best use of gear extension is to initiate the landing descent with the gear, allowing the increased drag to compensate for some of the forward weight component in the descent. Let's summarize these results. This summary shows that beginning the descent with gear extension allows an immediate flight path change with no bump, and a minimum change in pitch, attitude, and power setting. In addition, using the gear to initiate the descent minimizes the chance of landing with the gear up. The U.S. Air Force utilizes the term gear down, go down. This picture shows why using the landing gear to initiate the final approach descent requires a minimum change in pitch, attitude, and power setting. In the descent, the forward weight component always balances some of the additional drag due to gear extension, so a thrust change is required only to account for the difference between gear drag and the forward weight component. Since airspeed and therefore angle of attack is constant, the change in pitch attitude is equal to the change in flight path direction. We can now formulate the gear rule. To initiate the landing descent, extend the landing gear, and then set the final approach pitch attitude and final approach power setting. In this simulation, we are approaching the glide slope in a retractable gear light airplane, The target approach speed is 120 knots in order to keep up with jet traffic, with half flaps being the appropriate setting for this speed. The pitch attitude is 0 degrees and the manifold pressure is 19 inches. Slightly before intercepting the glide slope, we initiate the descent by extending the gear, then set the pitch attitude to -3 degrees and reduce the manifold pressure to 17 inches. The flight path is now established on the glide slope, and the airspeed remains at 120 knots. Note that by initiating the descent with the landing gear, the power change was only 2 inches of manifold pressure. This general approach profile summarizes both the flap and gear rules. Extending flaps to slow down during a non-precision descent is the first choice, since bumps in the flight path will not matter. A second choice is to extend flaps to slow down while in level flight, as long as the bumps in the flight path are small. Bumps are generally small if flaps are extended in increments, and the speed is allowed to stabilize before selecting the next setting. Generally, flaps are extended prior to the final landing descent, except in visual conditions, where they can be extended in order to slow down during a visual traffic pattern or when cleared for a visual approach with high ceilings and good visibility. Gear extension initiates the landing descent in all cases. These flap and gear rules are applied in the Instrument Approach Profiles video and the Visual Approach Profiles video that are part of this series.